Okay, in this problem we have a thin homogeneous bar. End A is able to move along a smooth horizontal surface, and end B is able to move along a smooth vertical surface. It's released from rest when theta is 36.87 degrees. Want to find out what the angular acceleration of the bar is once you let go. FBD, we're going to look at the forces that act on the bar. Not too many forces are acting because it's smooth. So this is going to be NA, I'm sorry, not NA, but NB. NA like this. And of course the weight force, homogeneous bar, it's right there in the middle. I'm going to put X positive to the right, Y positively up. Newton-Euler equations. So my first equation is going to be summing forces in X. We simply have minus NB is equal to MAGX. Second equation, summing forces in Y, we get NA minus mg is equal to MAGX. So this equation that I'm really going to use here is NA is equal to mass G plus AGX. And lastly, it's going to be a moment equation. I'm going to choose G because that's the one I usually fall back on if I can't easily find a fixed point. So summing moments about G, moment due to NB, it's going to be NB times L sine theta. It's going to be a plus K. NA, it has a moment arm of L cosine theta. It's in the minus K. And that's it. So that's equal to mass moment inertia about G times alpha. For a thin homogeneous bar, IG is 1/12 ml squared. So if I combine equations 1, 2, and 3, I get that NB, which is minus MAGX times L sine theta. I get NA, which is going to have a minus sign in front of it also. NA we saw was MG plus AGY. I need to fix up a typo here. This should be a Y as well as this one here. And that has a moment arm of, what do we say, L cosine. And that's equal to I alpha. So our Newton-Euler equations reduces down to a single equation. That's good. The bad news, of course, is we have AGX as an unknown, AGY as an unknown, and alpha. Kinematics, that's where we go. That's going to give us what we need. So what I'm going to do first is I'm going to relate the motion of A and B. So acceleration of B reference back to the acceleration of A. So this R vector is going to go from A to B. So we got minus omega squared R B with respect to A. It says that it's released from rest, so that's a 0. B is going to be moving only in Y, so I'm just going to write that as ABJ. A is only going to be moving in X, so I'm going to call it A sub AI. alpha. I don't know what it is, but I use the positive sign convention in the Euler equation. Got to use the same one here. And the vector which goes from A to B is going to be an L cosine theta I plus L sine theta j. And I cross alpha with R, group together my terms, and I get A sub A minus alpha L sine theta I. And the j component is going to be alpha L cosine in the j. So one vector equation, two components. I'm going to pick the x component. 0 is equal to A sub A minus alpha L sine. So A sub A is equal to alpha L sine theta with a plus sign. So this I'm going to use next by saying that AG as a vector is equal to A sub A plus the same alpha crossed with a vector which goes from A to G minus omega squared RG with respect to A. Release from rest, there's that. A sub A, that's just in the x, alpha k, crossed with the vector from A to G is going to be an L cosine theta in the I L over 2, and then an L over 2 sine theta in the j. So carrying all this through, I get A sub A minus alpha L over 2 sine theta in the I plus alpha L over 2 cosine in the j. Okay, so what we wanted was to get AGX and AGY in terms of alpha. So I see from here, therefore, the AGX is equal to A sub A minus alpha L over 2 sine theta. Above I saw that A sub A was equal to alpha L sine, so this becomes a plus alpha L over 2 sine theta. And AGY is going to be equal to alpha L over 2 cosine. Like that. So that's what we need. We got this equation to substitute in, this equation to substitute in. So therefore, the solve part, I put that back into my equation, and I get minus m AGX, which is alpha L over 2 sine theta, times L sine theta, minus mg plus AGY, which is alpha L over 2 cosine. This is multiplied by L cosine, and that's equal to the mass moment of inertia about g times alpha. So we see here we have everything now in terms of alpha. I can solve that, and what I'm going to have here is going to be a minus mgl cosine on top. On the bottom, I've got my IG. I know what that is. I'm going to have an m L squared over 2 sine squared theta. I'm going to have an m L squared over 2 cosine theta, like this. So this becomes minus mgl cosine Sine squared plus cosine squared is 1, so this becomes IG plus ML squared over 2. The negative sign means that I guess plus, and I was wrong. It's actually a negative in the clockwise sense. So the problem looked pretty basic. It was just a single bar constrained to move in a fairly simple way, but the kinematics actually became quite long. Let me check something here before we wrap this up. I want to make sure that because I'm pretty sure I left off a factor of 2. When I did my moment about G, I apologize for this mistake here. But what I have here, the moment about G is going to be L over 2. L over 2. So this becomes an L over 2. This becomes an L over 2. So this equation then reappears back here. So we have L over 2 here, L over 2. So there'll be a 2 factor there. There'll be a 4 there, and a 4 there. So the final result here is ML squared over 4 plus IG on the bottom. Anyway, what did we do here? The first step, the easiest one in this case, was a summation of forces and moments from our FBD. We got 3 equations. We reduced it down to 1. The thing that took the most time was the kinematics. The first kinematics equation was just to establish the fact that A and B are not free to move without constraints. A only moves in X. That was important. B only moves in Y. So from this we found A sub A in terms of alpha. Our goal, though, was not to find A sub A, but that was more to find the X and Y components of AG. And so that's from where the second one came. So then we had to relate A to B to AG, and that's where we got that. We substitute that back into a reduced Newton-Euler equation, and we got this.